So here we introduce the inductors and inductance. So if you have so most of you have studied the circuit analysis, so you know what an inductors when you need to calculate it. But here in a physics point of view, an inductor is a device that used to produce a known magnetic field. If a current I is established through each of the n windings of an inductor, a magnetic flux phi b links those windings, the inductance L of the inductor. So it is defined as this. L, capital L is the inductance, and it is proportional to the number of coil and the amount of magnetic flux. But it is inverse proportional to the current. So suppose we have same current for different inductor, and then we see which one can generate more magnetic flux. So it is the inductance. 圈就绕多少圈。So the SI unit for inductor is Henry H. So as an ECE student, some of you in the exam you still written the SI unit for a capacitor is something like C over V. I cannot say you're wrong, but for a capacitor, the SI unit is farad. It's F farad. Do not write C over V anymore. I cannot say you're wrong, but as an easy student, try to remember the SI unit is farad, and for inductor the SI unit is Henry. So this graph shows an inductor which is made by microfaraday, and actually it tells you that because you need to wind the wire into many loops so that you can increase the inductance of the inductor. So actually the wires should be insulated. They cannot touch each other, because if you have a loop and something like this, so this and this cannot conduct. The current should be go through the loop rather than going this way. So it need to make it insulated. And Faraday's insulate his wire by wrapping them with a strip cut from one of his wife's petticoat. So his wife is sacrificed. Actually, his wife's coat is sacrificed for the science. It tells you something like this. Actually, we have this definition for the inductor. So what we concern is the magnetic flux, and capital N is separated into small n times L. Small n is the number of turns per unit length, and L is the length of the inductor, and phi b is nothing but B times A. And in the chapter 29, we know that for solenoid, the magnetic field is mu0 times small I n, as mu0 times I n. So we substitute B into here. So we will get NL, mu0 INA over I is the inductance. And we move small l to the left side, which means we divide small l on both sides, so that the inductance per unit length is something like this. Mu0 is a constant, n is the number of turns per unit length, and A is the area. So that when you need to make a very large inductance, so the coil will be very large, and you also need to make um, the number of winding very large, so that you will have a large inductor. So here we talk about the self-induction. So if two coils, which we can now call inductors, with two coils, at least two coils, or many coils, are near each other, and the current I in one coil produce a magnetic flux, because as long as we have one coil, there will be magnetic flux. Well, we know it at chapter 29, according to the Ampere's law. And so if we have many coils, this coil will have a magnetic field and of course a magnetic flux. This magnetic flux will go through other coils. So that according to the Faraday's law or the Lenz's law, we'll know that for other coils, it will there will be an induced electromagnetic force on the other coil, and it will look like a voltage drop across the whole inductor. Here it's mentioned that we have seen that if we change this flux by changing the current, an induced EMF appear in the second coil. According to Faraday's law, an induced EMF appear in the first coil as well. This process is called self-induction, which means you have generated a magnetic field and magnetic flux. So the magnetic flux is changing. So for other coil, you will try to generate another magnetic flux so that to decrease this changing, or to try to stop this changing. This process is called self-induction, and the EMF that appears is called the self-induced EMF. It obeys the Faraday's law of induction, just as other induced EMF do. So in this case, we still have the original definition for inductance, and the Faraday's law is something like this, and we substitute and find B here, so that it will something look like this. The electromotive force is minus L didt, although when you learn in circuit analysis, it is something like V equals L didt. You can regard it as a negative electromotive force, which is a negative battery. So it is a voltage drop. So in this form, it is the voltage drop for the inductor. And this is what you learn in circuit analysis. But in physics, they try to write it like this. They like the EMF, and thus an inductor such as a coil, whether the current time. Okay. So we can simply derive the current and the EMF, something like this, which is a familiar result. So actually, we can also solve the RL circuit, and okay, for most of you have learned the circuit analysis, so this is very simple, and actually it's something like so this is E using the KVL, and the voltage drop for the resistance is IR and plus LDI dt. So you solve this first order constant ODE, and then you get I equals to this. So this is very trivial. And the tau L is called the time constant, which is L over R. So solving this is very easy. You just only need to substitute SL plus R equals 0. So S equals minus R over L. And then you know that I equals A exponential minus R over LG. This is the homogeneous solution, and actually the particular solution because it is a DC, so it is a constant. And then you substitute the initial condition, you'll find A and B will be E over R and minus E over R. A is minus E over R and B is E over R, so that actually you can get I to be like this. And for this case, it tells you that when the current of the inductor is climb to E over R, and then you try to remove the E, and then the current will be exponentially decay with the same time constant, something like this. So this is very easy. Any questions? Oh, actually, B is simply determined by just substitute B into here, so that E will be BR, but A is determined by the initial condition, so you get B equals E over R. Or you can use the Laplace transform to solve the ODE as well. So here's a sample problem. The figure A shows a circuit that contains 3 identical resistors with R, 2 identical inductors with L, 2 millihenry, and an ideal battery. E equals 18 volt. What is the current I through the battery just after the switch is closed? So when the switch is open, of course there will be no current going through all the 3 paths before the switch is closed. And actually, the current for inductor is continuous. So for easy student, I suppose you all know that very well, because one of the chapter in second is talking about the initial condition. But for other students, I need to mention it to you. And for capacitor, we for the capacitor is continuous. And for inductor, V is not continuous. And for capacitor, I is not continuous. I did not write it out, but I write the continuous variable for inductor and capacitor. I is continuous for inductor. V is continuous for capacitor. So in this case, for path 1, after the switch is closed, it's just closed, I1 should be 0. I3 should also be 0, because the current for the inductor should be continuous. So I1 and I3, I1 0 plus. Suppose this is t equals to 0. Okay, to be in the other direction. Okay, so suppose when t equals to 0, the switch is closed. So I1 0 plus equals to I3 0 plus equals to 0. So for the battery, I0 plus should be only the middle current, which is 18 over 9 ohm, which is 2A. Okay. So this is easy. So for part B, what is the current I through the battery long after the switch has been closed? So you can go back here. After the switch was closed long enough, then the current, well, VR. Okay, VR is actually proportional to I. So the current will settle somewhere, and actually the inductor will look like a 0 ohm, will look like a short circuit. So in this case, suppose the battery long after the switch has been closed, the L will be something like short circuit. So R equivalent will be R parallel with R, which is R over 3, which is 9 over 3 ohm. So the current going through the battery will be 18 over 3, which is 6A. Actually, you can simplify the current going through the to either of the inductor, something like uh, 2 times 1 minus exponential 2 minus t 0.22 millisecond, something like this. A tau L is of course L over R, which is 0.22 millisecond. 0.22 millisecond. Because this is a voltage source and these three branches are independent of each other. So you can see it like this. Then you can find the current going through the inductor with respect to time. So this is easy. So for the next sample problem, a solar has an inductance of 53 millihenry resistance 0.37 ohm. If the solar is connected to the battery, how long will the current take to reach half of its final equilibrium value? Of course, for first order, ODEs is exponentially decay or exponentially settle. And as you know, tau L is L over R, which is 53 times 10 to minus 3 over 0.37. So this will be 143.2 milliseconds. So we want to know, suppose it's settled at here, we want to know the time for the current going to half of it. We know we have something like I of t equal I0 1 minus exponential to minus tau L, something like this. If we want it is settled to half of it, suppose I of t equals I0 1 minus e minus capital T over tau L will be half of the steady state current. So I0 will cancel, and we multiply 2 on both sides, and we will find that exponential to minus t over tau L will be 0.5. And we will find that t will be tau L times log 2. So it is 143.2 milli ln2, which is around 0.1 second, which is around 0.1 second. So time is slightly less than the time constant, because e to the minus 1 is something like 0.6 something, I forgot 0.68 or I forgot. It should be something like 1 minus is 0.64. 0.63 is 0.63 minus 1. Something like this. So here we talk about the energy stored in a magnetic field or an inductor. So if an inductor L carry a current I, and the energy stored in the magnetic field will be something like UB is 1/2 Li squared. If you can still remember the energy stored in a capacitor is something like UE So a simple derivation for this equation is something like the du is the power, and the power is nothing but I times V. And as we know, V is LdIdt in the previous slide. So we try to calculate the total energy. So we integrate dUB from 0 to UB, and we substitute this into the integral. And actually, this is the chain rule. So that we'll have ILDI, and finally it turns out to be 1/2 of Li squared. Another sample problem. So a solenoid has an inductance of 353 millihenry, resistance 0.35 ohm. If a 12-volt EMF is applied across the coil, how much energy is stored in the magnetic field after current has built up to its equilibrium value? Okay. So this is pretty easy. Okay, actually, UB, sorry. Actually, we calculate the I. The I in this loop will be nothing but 12 over the resistance 0.35 according to the Ohm's law. So the current is 34.38, and UB we can use 1/2 Li squared will be times 53 times 10 to minus 3 times 34.3 squared. So this is 31J. Any questions? So, so it asks you how many time constant will halve its equilibrium energy to be stored in the magnetic field. So, we want to have half of the energy to be half of Li squared, but it is half energy. Of course, the current is not half, because if the current is half, the energy is 1/4, because there's a square for the current. So actually, we want to have half of the original energy, which is 1/2 of Li squared. So we can know that I half should be 1 over square root of 2I. Actually, I equals capital I 1 minus e to the minus t over tau L. And we want it to be 1 over the square root of 2I So with some calculation, we can know that T half will be something like tau L times Ln square root of 2 over square root of 2 minus 1. Which is tau L is 143.2. 143.2 times 1.23. So it is So it is 176 millisecond. Or actually, it asks you how many time constant. Actually, it is 1.23 tau L. Should be a more suitable answer. So next, we talk about the energy stored in the magnetic field again. But now it is about the energy stored in a unit volume. And actually, we can derive it like this. UB is what we derived previously. And it is the total energy stored in the inductor or the magnetic field. AL is the volume, is the total volume. So we try to calculate the energy at unit volume. And UB is 1/2 of Li squared. So we have this term, and capital L over L, we put it to the front, and we have I squared over 2A. So we just rearrange the order of them. L over L is mu 0 times n squared A. In the previously we discussed. And B is mu 0 in for a solenoid. So we can just substitute this term into here, and actually we have I equals B over mu 0 n, so that we substitute into here, and finally A can be cancelled. Here we have mu 0 squared, here we have mu 0, but this is at the bottom, so 1 mu 0 is left, and n squared, and n squared is cancelled. So finally we get UB is B squared over 2 mu 0. I'm not sure whether you can still remember in the electric field, UE is something like 1/2 epsilon 0 B squared, because you don't need to memorize all the formulas. I'm not sure whether you still remember it. But they look quite similar. E chained to B, epsilon 0 chained to 1 over mu 0, and 1/2. And actually we'll use this result in chapter 33 in the EM wave. So finally, this chapter mentioned about the mutual inductance. Mutual inductance is something like you have two inductor. So actually for coil 1, suppose you have a battery and a resistance, so that this inductor will generate magnetic flux through this inductor, and this magnetic flux will go through another inductor, and this one we don't really have a battery or a EMF. It's only an ammeter, but we'll know that there is some current going through this loop because there are changing B field or changing magnetic flux through this second coil, the coil 2, so that you induce a EMF on this loop. So similarly we can define the mutual inductance like this. For a single inductor, suppose we ignore this part, we will have di times di dt times L will be the electromotive force. But here we will have the current at the first loop times this is the mutual inductance, which will generate the electromotive force at the coil 2. So coil 1, the magnetic flux will generate an electromotive force at the coil 2, and symmetrically, if you have a source at the second loop, so this magnetic flux will generate electromotive force for coil 1 similarly. And this is called the mutual inductance, denoted as capital M.